Energy and power, the essentials. Energy and power are another example of rate versus quantity. Quantity could be something like 10 kilometers. A rate based on that would be 10 kilometers per hour. Here is a simple example, a mature example of the difference.
I ate 2 cookies.
This is a quantity.
I eat 10 cookies a second.
This is a quantity rate. However, telling a person you ate 10 cookies a second doesn't matter if you don't know what the cookies are.
I ate 6,000 calories of cookies today.
Now it is an energy rate. In metric, we would call this joules per second, and it's nicknamed the watt. So the minute you see a watt, change it to joule per second, and you will understand it.
I eat 10 megajoules per day.
That is power in metric. Energy is measured in joules. It's a quantity, the ability to do work. Energy and work are basically the same thing. You use energy to do work. Power is the rate at which the energy flows, joules per second. But because it was given a nickname, the watt, it hides the fact that it is a rate, and people tend to think it is a quantity. 60 watts means 60 joules every second. Power is energy over time. Square brackets again mean we're looking at the units. Joules per second is identically equal to a watt. To avoid misunderstanding, whenever you see the watt, immediately write joules per second in its place, or do it in your head, or you will confuse it with a total. I guarantee you, unless your parents are engineers or teachers, I wouldn't guarantee it if they're teachers, they will think a watt is a total. It is very misunderstood. Your power. We like to say, oh, you're as bright as a 116 watt light bulb. Well, when I was a kid, we'd say, you're as bright as a 10 watt light bulb. Now, if someone did that, you go, oh my God, it's 10 watts, it's blinding me. Because the bulbs are different efficiency now. A 10 watt light bulb is exceedingly bright because you're actually getting much closer to 10 watts of light. The old yellow ones that you see pictured here, they waste like 90% of their energy in heat. So a 60 watt desk lamp today is often only like an 11 watt LED. So the idea of saying, you're as bright as a 10 watt light bulb, now you would say, thank you. I had no idea I was that luminous. And if you say you're as bright as a 10 watt laser, man, you're cutting. You're blindingly bright. So the wattage doesn't necessarily tell you how much useful power you're getting. So anyway, when I started my teaching career, the average Canadian ate 10 megajoules of food per day. We're such now, we do 14. Canadians are eating 40% more on average than when I started my career. And it's all due to me. Now, when we want to do power, we got to do time in seconds. When you become a social reject and you have no friends, and you study in physics or something, you will eventually memorize there are 86,400 seconds in a day. So if you take the 10 million joules you eat, you divide it by 86,400 seconds, you will find you are 115.7 joule per second light bulb, which by definition is 100 and roughly 16 watts. So you, my friends, are as bright as a 116 watt light bulb. The idea is to make sure you know the difference between quantity and rate. So if you look at these two pictures and someone says, hey, is that a lot of water? And you go, well, it's a cup. That's how much water is. Golly, a cup. I can see through that water. It's nothing like the water down where I come from. It's like, it's not wriggling or nothing. Now this thing on the left, which is that one of them fancy faucets? Is that a lot of water? Well, how long you plan to leave it on for? Oh, I could look at that all day. It's like, no, there's no total here. It depends on how long you let it run. Now we get to these two. You go, golly, he's filling the swimming pool. That's cool. This guy over here in the left, he'll never fill the swimming pool without a little hose. This guy will. Well, no, both hoses can fill a swimming pool because there's no You can't go, there's not enough water in that hose. It's like, it's not a total, it's flowing. This will fill a swimming pool in about an hour. This will fill in a swimming pool in a couple of days. Now, some students are smart enough to be dumb, and you would go, well, no, it'll never finish the filling a swimming pool, it'll evaporate. Don't take the metaphor too far. The idea is, can you distinguish that a rate cannot be confused with a total? It makes no sense at all. But you will do it frequently as long as you write the rate as a watt. When you see it as a joule per second, you'll get it. You tell your younger sibling that you got a job paying $20 an hour, and they'll go, gee, is that a lot of money? And you go, well, no, stupid. It's $20 an hour. If I work for 1 hour, it's $20. If I work for 4 hours, it's $40. Can you tell me why it's possible that a person being paid $20 an hour can actually make more than a person being paid $35 an hour? So this person is not necessarily being paid less money than the other person. They're being paid at a lesser rate. If this person gets 8 hours of work on a day and this one only gets 3, the rate cannot be turned into a total until you know the time. Here's another one that oddly enough trips people up on rate. $60 is not the same as $60 an hour. It's just a coincidence that the numerical values are the same. But that would not be like, I'm like freaking out, man. I'm 38 years old today and my body temperature's 38 degrees. Is that like an eclipse or something? Like, it's just a coincidence. They're not measuring the same thing. Would it be like, hey, skater, if we were traveling for like 100 kilometers and we were going 120 kilometers an hour, does that mean we passed it already? No. Get the concept straight. When we switch to metric power, confusion is going to occur because the rate gets hidden in joules per second being transformed into watts. So your conceptual switch, always switch out W with joule per second so you know that that is a rate. This is what you can trip your parents on. What uses more energy, a 10 watt or a 40 watt light bulb? It's not a total. That's again like saying who earns more money, $20 an hour, $35 an hour. It's like, that's not a total, it's a rate. You have to tell me how long. Take the 10 watts, change it to 10 joules per second. Take the 40 watts, change it to 40 joules per second, and you instantly can tell. The 40 watt bulb is using energy at 4 times the rate of the other one. But if the 10 watt bulb is left on for 5 hours and the 40 watt bulb is left on for 1 hour, the 10 watt bulb uses more. Try it on your parents. I guarantee you they will automatically say the 40 watt bulb uses more energy, and you can go, aha! And you can lord your intelligence over them. Any energy we've used in this course, you can divide by time and get the power. Whether it's the general statement for work, an expanded statement for work, work due to gravity, work due to friction, work due to stretching a spring, which is grade 12, or kinetic energy, and of course can use the heat formulas. You can even use Einstein's formula in there. It doesn't matter. You divide it by time, joules per second becomes watts. There are special cases where we prefer to talk about watts, power, rather than joules. And we so often use watts, we have allowed a nickname that is not official. People will talk about wattage and they will talk about voltage, but you never talk about kilometerage, right? We don't do that. You don't talk about joulage. You don't talk about newtonage. So sometimes we allow people to say wattage. When do we refer to watts rather than total? When there is no total. If you think about it, the sun doesn't stop shining. There's no total energy in the sun. It keeps on coming. A battery will run out. So a battery is like a canteen, but rain is falling continuously. Sunlight is falling continuously. So sources that don't run out, like the electricity in your house, the water in your pipes, we're better off talking about the flow rate, not the total. And that is why all appliances that plug into the wall get rated by their wattage. How many joules per second are they drawing? Because there is no total there. The flow rate on your house, the water keeps flowing. Some houses have lousy water pressure, some have great, but you don't have a tank of water that you're going to run out of. So flow rate is often used in place of energy in situations where it never runs out. We're just concerned about how fast can we do the job. Let's take a look at an example of work versus power. A strong man can produce lots of energy. A powerful man can do it quickly. When you do aerobic training, you are working on an energy flow rate. You are trying to sustain a power output. If I set this man up to lift a 100-kilogram mass up the cliff, 20 meters, okay? He has to pull with 980 newtons for 20 meters. So when we want to calculate the power, the first thing we have to do is calculate the energy he needs to produce. So he needs to produce 19,600 joules of energy, and we give him 180 seconds to do it, 3 minutes. This gives him a power output of 108 joules every second, 108 watts. Suppose he trained at this a lot to the point he could pull the weight up and never actually fart, which I suspect is a real risk in this posture he has. And he reduces his training time to 20 seconds. What will change? The energy he needs to produce or the rate at which he needs to produce it? Well, we look at our formulas for the story they tell. MGH doesn't care how long you took. So the energy output will be the same, but if he can do it quicker and reduce the denominator, he will output the energy faster. He will increase his wattage. So when you become more powerful, you are increasing your flow rate of energy. You are basically becoming higher wattage than before. It's a strange way of looking at it, but much of the gymnasium equipment that's electronic will actually allow you to measure your power output. Though the joule per second or the wattage one is not favored, so only some equipment allows you to select that. Most of them do like calories per hour. They don't use joules per second, but you can find it on some of the gym equipment. It will tell you the power you are producing. If we go back in time prior to metric, there are two units that I think are amongst the greatest units ever created in history: the horsepower and candle power. Candle power is disappearing, but when electric lights came out, Edison could advertise a light as 10 candle power to convince a person this one light bulb would replace 10 candles in their home. It's a great way to sell or help a person conceptualize something. When Watt wanted to replace horses with the steam engine, he coined the term horsepower. And what a beautiful, evocative description of that it was. Watt took a big horse. He picked a 550-pound weight for whatever bizarre reason. People in prior centuries go like, yeah, can you give me a 12-pound weight, a 7-pound weight, and a 27-pound weight? It's just like, what's wrong with powers of 10? Oh gosh, it's not complicated at all. So James Watt picked a 550-pound weight. He had the horse pull it up 1 foot in 1 second. Now, he didn't make the horse do that. The horse just pulled. And the horse was able to lift a 550-pound weight 1 foot in 1 second. And Watt called that a horsepower. And can you imagine him selling this to some farmers?
So what you're telling me is the 10-horse team I've got, you could replace it with one of your 20 horsepower motors and I wouldn't need the horses no more.
And he's like, yes. So it was a great way to sell his steam engines by horsepower. And as the centuries went by, we liked his invention so much, we actually named the metric unit of horsepower after him, Watt. So Watt invented the horsepower, and we invented the watt to honor Watt for inventing the horsepower. Isn't that cool? Now, what is a horsepower in metric. It turns out to be around 750 watts. So this horse was able to pull 750 joules per second. So if someone says, "What kind of horse do you want?" "Oh, I want one of those 1,000-watt horses." People will be like, "Huh?" But it would be a legitimate unit. Watts and horsepower are the same thing, the same concept, just in different systems of measurement. So let's turn our attention to a Honda Odyssey again. We want to figure out what the wattage of this car is. So when I look up the mass of my Honda Odyssey, that's the mass of the vehicle. This is the mass of a driver. We'll combine them. And according to Car and Driver magazine, in my footnotes, I like my cute little symbol, the Honda Odyssey went from 0 to 100 in 6.6 seconds. There's a Car and Driver quote. So that's not Honda, that's an independent agency did this. So we want to compute the power output of the Honda. Well, once again, to do the power, you need the energy. To use the energy, you need one of two things. Work is force times distance, or EK equals 1/2 mv squared. Once again, there's the hard way, there's the easy way. Which way would be easiest here? Since we've been told the final speed, the easiest thing to do would just be use 1/2 mv squared. If you had to do force times distance, you would have to compute acceleration first, compute force, compute work. You'd get the same answer, but it takes 3 steps. This takes 1. So we're looking at about 800,000 joules being burned to get the car up to highway speed. What kind of power is that? Well, if I take the joulage, the energy, divide it by the time, we find out that the Honda Odyssey is producing about 122,000 watts. We can call that 123 kilowatts. That would be really odd to term a car in kilowatts, but the Europeans do it all the time. The horsepower is done. Now, if I take 123 kilowatts and we use the last slide that said that a horsepower is 700 and roughly 50 watts. If I take 123,000, I divide it by the 745 watts in a horsepower, I get 164 horsepower. So according to this observed behavior of the Honda Odyssey, it is a 164 horsepower engine or 123 kilowatts, meaning it is burning 123,000 joules every second. But when I look up the Honda Odyssey, it says it's 208 horsepower. So, whoa, are they ripping us off? That's a fair difference. So, who's correct? Honda advertising 208 horsepower or our calculation from observed behavior of 164? Well, the question is, where was the horsepower measured? When they measure the engine horsepower, they measure it directly off the motor drive shaft. When we're measuring the horsepower, we're measuring the observed behavior on the road. And between the engine to the wheels, there's a lot of mechanism. And the standard rule of thumb is that you lose about 80% at the engine, and then at the engine, you lose another 15% till you reach the wheels. That's a rough industry estimate. So this 208 horsepower, Honda already measured it at the drive shaft. We don't have to worry about engine efficiency. But now we lose 15% of their stated value till it gets to the road. So if I take Honda's measurement and I lower it to 85%, throw away 15, keep 85, I get 177 horsepower. So a simple high school calculation, and knowing that we have to just look up what kind of drivetrain losses are, we get within 92% of an actual real world measurement on the vehicle. So Now you're starting to see you've got some real world power. So not bad. Not bad at all. Humans, you can read this. We're running somewhere between 1 and 4 horsepower. Now, an elevator problem is about the most advanced power problem I could give you. So we got two buildings, the Skyview Towers and the Squats, and they're getting new elevators. Each building wants to get tenants to the top floor in less than 60 seconds. What power or wattage of the motor is required in each building? Well, once again, the formula is power is energy over time. But we have to go ahead and compute the power by getting the energy. And the energy is figured out by mass times gravity times height. Where did I get the mass of the elevator from? Got the mass of the elevator by inventing these numbers. I looked up a standard elevator car is about 1,200 kilograms, and with about 400 kilograms of human meat, living and talking, right? It's not a slaughterhouse. So this makes the elevator cab about 1,600 kilograms. And in industry, the counterweights inside the elevator shaft take about half the weight away. So this elevator shaft really only needs to lift 960 kilograms, all right, which is really nice. They offset the weight with these counterweights. So I've set it up here where you have to go, oh, it's 960 kilograms. So if you lift 960 kilograms on Earth for 90 meters, you get 86,400 joules. Now, if you do that in 60 seconds, you get 14,400 watts. So the first building would need a 14.4 kilowatt motor. If you want to do the other building, you substitute in 200 meters and nothing else changes. So you will find if you get to the top of a building and are ever allowed to see in the elevator shaft, you will see the motors can get quite larger for the taller buildings, not because they're necessarily heavier, right? Even as the elevator gets bigger, they add to the counterweights. There really shouldn't be a lot of weight difference being thrown around. It's passenger count. So a short building and a tall building will have their elevators balanced to the same rate. The difference is the taller building has to get that elevator up there at a faster rate. Otherwise, you're going to be waiting all day. So what you may notice is tall buildings get faster elevators. And the shorter the building, the cheaper they seem to make the elevator. You could put a 5-watt elevator and make it work. Put a 5-watt motor in, but the people will be going up your building with a and they'll make it, but it'll be days or weeks. And that's something I've always thought with handicapped people, they get really screwed. Because if you ever notice, if you go to an apartment building, the elevators move like a bat out of hell. But when the handicapped people get in the lift, they use the cheapest frickin' motors they can find, and they're in their wheelchair lift, and it's going as this tiny itty bitty motor. And it's like we're telling handicapped people, you don't have anywhere to go quickly. So I've always thought that that's kind of a ripoff, that people in wheelchairs get the crappiest lowest power motors we can give them. So the higher the wattage doesn't mean it can go higher. It simply means it gets there faster than before. And that's all you need to know about power in grade 11.